The purpose of exercise 8 is to write a Python function that will take a matrix as input and will output a Boolean, so true or false, depending on whether that matrix is symmetric. So it should output true if the matrix is symmetric and false if the matrix is non-symmetric. And of course, keep in mind that small computer rounding errors and so on, you know all about this. I've mentioned this several times. Okay, this is an important um, exercise because the function that you will write here is going to be used by several of the subsequent exercises. So in the next several exercises, you're going to be using this function that you create here. Okay, and then we want to test it with symmetric and non-symmetric matrices. Now, there are many ways that you can solve this uh, problem. There are many solutions that you can come up with. I'm going to now switch to Python and show you one solution, but I don't want you to think that that is like the only solution or the best solution. If yours works, then that's good enough. Any solution that you would come up with is based on the same underlying principle. And that principle is that if the matrix is symmetric, then it should equal its transpose. So if S is symmetric, then S equals S transpose. If S is non-symmetric, then this is not going to equal its transpose. So that's the basic idea. That's the theory. And anything else you build up off of that is just, differences in algorithm implementation and so on. Okay, so what I do is compute a difference matrix. So S minus S transpose. And by the way, this will already crash if the matrix is non-square, which is fine because only a square matrix can actually be symmetric. Okay, so then I get a difference matrix. And here what I do is compute something called the sum of squared errors. So I square all the elements in this difference matrix and then sum them all up. So this is actually like a norm of the matrix. So it's like I'm computing a norm. Now the thing is, in theory, this should be the zeros matrix. In practice, we want to allow for some tiny little rounding errors and so on. So what I expect, therefore, is for this to be really, really close to the zeros matrix. And that's why I have code like this. So then I say, this is the sum of squared errors. And here I say, if that sum of squared errors is less than 10 to the minus 15, so this is my level of tolerance. If this is true, then, or if this is the case, then it's going to output a Boolean true. And if these are larger than basically, 0, really tiny number, then it's going to output false. Again, there's several ways that you can implement this. You can set the tolerance to be based on the singular values of the matrix. That's something you will learn about later in the book in the section on SVD, singular value decomposition. Okay, and then, here I have a note. You can also use is close. This is also a nice function. So this is the function. And now I'm going to test it on a non-symmetric matrix and a symmetric matrix. Okay, so we expect the result to be false and true because this is not symmetric and A transpose A obviously is symmetric.